technically the last lesson of week 6, but the lesson 20 will come, should be coming before the end of the week. So that way we're not having to speed run through too many things in our last week of classes, which is next week. And this will be Callister chapter 16, composites. So first we're going to name the 4 divisions of composite materials and cite the distinguishing feature of each. We'll cite the difference in strengthening mechanisms for large particle and dispersion strengthened particles reinforced composites. We will distinguish between the 3 different types of fiber reinforced composites on the basis of fiber length and orientation. And we're going to comment on the distinctive mechanical characteristics for each type. We're going to calculate longitudinal modulus and longitudinal strength for an aligned and continuous fiber reinforced composite. We're going to compute longitudinal strengths for discontinuous and aligned fibrous composite materials. And finally, we're going to explain the structure of laminar composites. So this is something very near and dear to my heart because my research, as I've discussed many times before, you're probably bored of hearing me tell the story of it at this point, but my research for my master's degree was in ceramic composite materials. So I've had to take advanced courses on this subject, and I've done research in it, so I know a little bit about it, which is nice. What's cool about composites is it's such a huge branch of material science, and it's a very exciting branch. You can do so many great things to create brand new, almost exotic materials just by taking materials that we have available to us and mixing them together in specific ways. And so we're going to talk about how we can do that, how we can get the best of both worlds in many cases between a very brittle material versus a very tough material. And we'll try and find balances between them. So a composite, let's see, actually, I need to stop here, and we're going to switch to the board first, because I'm going to have some concepts that we'll cover together on the board, but then the rest of the lecture will be on the PowerPoint slides. Okay, so composites. So far, we have learned about different materials. And you can think about what materials those have been. Metals, right? We've talked about ceramics. And a little bit early on in the semester, but especially in our last lesson, we talked about polymers. We've talked about what makes them great and how they can be used to solve different problems, in their own rights. And also, different calculations regarding each one. I've tried to give you an understanding of how each material is made up starting at the atomic level, right, and then moving into the nanoscale. Or, I'm sorry, the microscale. So the question is now, what if you combine them? What if you combine them? And that is what composites are. Okay. So composites, they are composite. So composites. These are a combination of 2 or more individual materials. Two or more. So you could have a whole bunch of materials that are involved in the making of a composite. And we've heard about a lot of different kinds of composites in our daily lives. You can probably think of a few right now off the top of your head. But these will include things like fiberglass. Okay. Things like carbon fiber. Another one that I can think of is technically duct tape. Duct tape is a composite. Especially if you think about how the way duct tape rips. You can think about that it's a very interesting concept. It's got an adhesive layer, and in between that adhesive, it has a fabric, right? So a fabric surrounded by an adhesive, which makes it a composite material. That's not to say all things that are like, you wouldn't necessarily call a car a composite, like a whole car. We're mainly talking about a type of material, right? And then, of course, you have my old research, silicon carbide fiber, silicon carbide matrix, ceramics are also a composite. Okay? These are just some examples, right? So why do we do this? Why do we want to create things like fiberglass or carbon fiber or even our silicon carbide fiber, silicon carbide matrix ceramics? Well, our goal is to obtain a more desirable set of mechanical properties and it's up to us as engineers to decide what do we mean by more desirable, right? Maybe we want it to break at a higher tensile strength. Maybe we want it to break at a lower tensile strength. Something that's more desirable. A more desirable combination of material properties. Okay, so that's our goal. That's what we're aiming for when we talk about composite materials. Okay, so let's talk about some classifications and terminology. So a composite is a multi-phase material that is artificially made. Okay, so if it's naturally occurring, we don't typically refer to it as a composite. So that usually rules out things like metals, right? Because metals, steel, for example, could be considered a composite of different like phases of steel. So we don't really consider steel a composite material. So really, we're talking about on the macro scale. That's kind of what we're talking about at a scale that we can see. It's a material that is artificially made. And the matrix part, so there's usually always two distinct phases in the material. We have a matrix, and that matrix is the continuous medium that surrounds whatever's inside of it, okay? So fiberglass, for example, you've heard of fiberglass before. What is fiberglass? Well, fiberglass is literally long strands of glass fibers that have been embedded into a plastic or some kind of polymer matrix, okay? What is carbon fiber? Well, carbon fiber is the same thing, actually. It's long carbon fibers, in some cases carbon nanotubes, that have been submerged into a polymer matrix. So those are very, very common, is these polymer matrix composites, because that polymer adds a large degree of lower weight, basically. Like usually your low weight, high performance, like Formula One racers will be filled with carbon fiber and maybe some fiberglass components. So the matrix is a continuous medium, and then we have a dispersed phase, okay? This is a discontinuous and medium that's surrounded by our material. This is a discontinuous material that is surrounded by the matrix material, okay? So in this, like, let's say this is fiberglass. Here's our strands of glass fibers, okay? And they're surrounded by a polymer matrix of some kind, right? And that's what we're looking at here. Okay, so here on the right, we can actually see, this would be more like, in my opinion, the ceramic matrix, ceramic fiber, ceramic matrix composites that I worked with looked just like this. So that might be what these are. And what you see here is they've actually woven the fibers together to create a quite literal fabric. And then they glue that fabric together with a matrix material. So in my case, these were silicon carbide fibers of high purity that were glued together using a silicon carbide matrix of very low purity. Okay, so you can actually save a little bit on cost when it comes to strength. Also, the material behaves differently when it's actually made in this manner. It's stronger in the tensile direction for the fibers. Whereas the matrix material is more prone to cracking, and so cracks actually don't want to move through these fibers because they're very high purity. So the matrix phase, the purposes of the matrix are to transfer stress to the dispersed phase, okay? If I apply a tensile load to my matrix material on the outside, that load gets transferred to the fibers that are inside the material. So it transfers stress to the dispersed phase, and it protects the dispersed phase from the environment. Now, we did not talk about galling. Well, we talked a little bit about galling, but other forms of like oxidation and deterioration to the environment. But there's like a lot of materials that will react with air and salt water and like high temperature fluids of some kind, and that will cause them to deteriorate. When you protect it, you could protect it, for example, with a plastic. Plastic is very resistant to corrosion in many cases. And so you can actually protect it from some kind of hostile, toxic environment that it might be operating in, like under seawater, for example. You might be thinking about the Titan sub at this moment, and I have many opinions on that, but this is not the time. Okay, so we have three different kinds of matrix, matrix materials, but three different kinds of composites, and they're usually referred to by the type of matrix material that are involved. So we have a metal matrix composite, a ceramic matrix composite, and a polymer matrix composite. Usually the matrix is always made of just one material. The dispersed phases can be a whole bunch of different stuff, but usually you only see one kind of matrix material because it would be difficult to create multiple matrix materials in the same kind of system. It would be very difficult. And now we have our dispersed phase. So we just talked about our matrix phase. Here's our dispersed phase. And for the dispersed phase, we have different kinds of... for one thing, we have many different kinds of geometries of dispersion we can use, and then we can actually alter the different kinds of materials used, right? So the purpose of our metal matrix composites is to increase our yield stress, our tensile stress, and to add creep resistance. Ceramic matrix composites actually increase our fracture toughness. And our polymer matrix composites increase our Young's modulus, yield stress, tensile stress, and creep resistance, okay? And these are specifically referring to the dispersed phase. So these are the materials in the dispersed phase, okay? I don't think that these should actually be MMC, CMC, and PMC here. Technically, they should say technically DC, right? Metal dispersion composite, something like that, right? This is kind of confusing the way this is written, but our metals increase our yield stress, tensile stress, and creep resistance. Ceramics increases fracture toughness. And our polymer matrix composites increase our Young's modulus, yield stress, tensile stress, and creep resistance. We can have mainly three different kinds of dispersed materials. This is talking about the geometry of those materials. So we can have particles, fibers, which you see here, or structural. Okay, what is structural? Well, you could technically refer to rebar as kind of like a structural material, things that are mounted together inside of a system. Really, you could look at rebar as a fiber as well, but we'll cross that bridge when we come to it. Okay, here's a really big chart that is just kind of a giant zoo of composite materials that you can run into. And this is nice and handy because it actually classifies different types of composites by geometry. So we have composites. On one end, we have particle reinforced composites, which can be separated into large particle or dispersion strengthened. Okay. And that would be the difference between how big these particles are. So imagine taking a bunch of marbles and throwing them into a pot of glue and letting the glue solidify, and you still got the marbles inside, right? And what that does is you've now added particles to your glue, and it will change it actually changes the strength of that glue just because you've added those marbles into it. And it's certainly changed the weight. We have fiber reinforced composites, and so these can be continuous and aligned fibers. So like this would be a good example of what you would call a continuous and aligned, because these fibers are all aligned in one direction, and then you have a cross weave, right? So they're also aligned in a second direction, right? But if you were to put stress on the diagonal, that's going to change things. We will move out of kind of an isotropic system, right? If we think about back when we were discussing isotropy versus anisotropy, adding these fibers and these configurations can wildly change how isotropic or anisotropic it is. In our last lesson, I talked about carbon. Hold on. Maybe a few lessons ago at this point, I talked about carbon nanotubes, and actually, no, that might have been the last lesson. And they said that in the X and Y directions, it was resistant to stretching, but in the diagonal, it stretched quite a bit. Okay. Well, that weave is very similar to the weave we see here. So that's something that you can keep in mind when you're talking about directionality of material properties. So we have continuous and aligned composites, or fiber reinforced composites. We can also have discontinuous or short fiber reinforced composites. And these discontinuous or short fibers, little whiskers, these can either be all aligned in the same direction, or they can be randomly oriented, chopped is what we call this actually a lot in like just typical layman's terms. Chopped orientation is where you just chop these things up and they get mixed in random orientations. Usually, if you are 3D printing in carbon fiber, which you can buy 3D printing filament that is carbon fiber, this is the kind of composite that you're dealing with. It is a randomly oriented, discontinuous fiber reinforced composite. Okay, this is probably the most isotropic of all of these. Well, actually, your particle reinforced composites are probably pretty isotropic as well, but everything else is not. Okay, randomly oriented is going to be one of your most isotropic materials. Okay, we can have structural composites, which are like laminates and sandwich panels. Okay. Those of you who took mechanics of solids with me last semester will know what sandwich panels are, because one of our teams actually used a sandwich panel design for a beam on our beam competition. It was a really great design. And that was a sandwich panel design. Technically, you built a sandwich panel structural composite. And we're going to talk about what those are exactly. Like the Trident gum that you see here is actually technically a sandwich panel composite. They say not quite a composite material. I would say this is a composite material, technically speaking. Okay, so sandwich panels. And then you also have laminates. And laminates are basically, you have thin sheets of material that you then lay right on one on top of the other on top of the other. So imagine for a moment you have this weave pattern and you have a thin sheet of it, and then you take a second weave pattern and you lay it right on top, and then a third and a fourth and a fifth, and you just stack it up like that. Now you have a laminate material. What's cool about laminate materials is that you can actually stack these in differing configurations. So you could have one that's oriented in this direction, okay, so up and down. Then you stack the second one at just a slight degree offset from that, okay? And then as you stack them, you continue all the way around the loop. Why would you do that? Why would you want to do such a thing? And so finally we have nanocomposites, and we're not really going to focus too much on those because it's not really the focus of this course. This is like a heavily researched material science domain that we don't need to cover, because in reality, in your actual places of work, you're probably going to be dealing with all of these, right? If you go into automotive, you're probably going to be dealing in fiber reinforced composites. If you're dealing in aerospace, you're probably going to be dealing more with these structural composites. You'll be dealing with both, actually. And then in particle reinforced composites, if I'm being completely honest, I don't know of very good applications of these. I'd be interested in hearing more about them. I just don't hear about them often. Like I worked in these continuous aligned fiber reinforced composites for a long time, and I would hear about, actually, they were also laminated. So they were continuous fiber reinforced composites that were laminated in a structural way. So they technically fell into both of these categories. But, I never really heard of serious applications for particle reinforced composites, but they do exist. Okay, so here are some examples, though, of particle reinforced composites. And here they're talking about spheroidite steel. Okay. Like, we already said that natural materials don't really count, but we'll go ahead and give it to them. Spheroidite steel, because we have the spheroidite that's embedded in a ferrite matrix material, right? So the ferrite is actually quite ductile, whereas the cementite particles are quite brittle, and this creates a composite type material. Okay. We also have cemented carbide. Okay. So we have these brittle and hard WC particles, WC/cobalt. Not sure what WC stands for. And then we also have our cobalt matrix, which is ductile and tough. Okay. So similar idea. The ductile material is the matrix material, but the harder material is the particulate. And then we also have an example of automobile tire rubber, where we have a rubber, like just a regular rubber matrix material, but with carbon black particles, okay, that are embedded inside of the tire. And that actually is a stiffening agent, okay? A fun side effect of the fact that you add carbon black particles to your rubber matrix is that it makes the tire black. Right. So we didn't really talk about it much, but you can add in what are they called? I forgot the exact terminology, but they're like diluting agents in a way. But you add them in just to add color, and you can do that with polymers. And in this case, with polymer composites. Okay, so we're still in particle reinforced. So concrete is a particle reinforced composite. Okay, so there's a great application that I didn't think of. And this includes gravel, sand, cement, and water. Okay, so why do we use sand and gravel? Well, because sand fills the voids that we form between our gravel particles. So we have gravel, which handles most of the load, but to improve the concrete even more, we add sand, because that fills the gaps in. And then we have cement that kind of is there. It actually just binds it all together. So, and then you add water, of course, so you can make it actually fit into the shape that you need, and then when it dries, it solidifies because of the cement. We have reinforced concrete. So this is something that it's kind of like, yeah, this is particle reinforced, but are we really in the structural side now? Because we're talking about reinforced concrete. We reinforce it with a steel rebar or a remesh. We could even add a mesh. This will increase the strength even if the cement matrix is cracked. So the thing about cement well, really ceramics in general, but also the thing about concrete is it's much weaker under tension than it is in compression. You can put a lot of weight on it in compression, but if you try and pull on it, it'll break quite easily because it's so brittle. And so you can reinforce it with rebar. And what that does is, if it does actually have some kind of tensile force pulling on it, it's not going to crack and break as easily, okay? And even if it does break, it's not going to fall apart on you. You don't want your, concrete bridges that we drive over all the time to just suddenly break. So we can reinforce it with steel rebar or remesh. This would actually technically put it in the fiber reinforced category. We can also pre-stress the rebar. So actually, if we take our rebar and we pull it really hard, we put it in a lot of tension, we put it under some elastic strain, and then we pour our concrete over that rebar and let it solidify while we hold that force over a long period of time. When we let the rebar go, it's going to pull in our concrete. Okay, it's going to actually put our concrete into compression, which is really cool. Because what that means is, for a tensile force to be applied to our concrete, we actually have to pull it beyond the compression force before it feels any tension. Okay, so that's actually called pre-tensioning. Okay, so we have a rebar or remesh placed under tension before setting of concrete. We release the tension after setting, and it puts it in a state of compression. And to fracture concrete, our applied tensile stress must exceed the compressive. Okay, so I just explained all that. Okay, and we can also have post-tensioning, which doesn't work as well, but we can do it. Post-tensioning is where we tighten nuts on either end of the rebar to put it under compression. And this has issues with it, not the least of which, a lot of times these nuts like to come loose, right? So you have like a threaded rod here in this case, which could be considered like a piece, like a type of rebar. This takes a lot more work too, because you have to go around and tighten each bolt. And imagine with a fairly large object, you'd have to go in and do it. Whereas pulling them all at the same time might be a lot easier, depending on what you're looking at. Okay, so when we're taking a look at material properties, okay, and for our particle reinforced composites, we can actually use what's called the rule of mixture, okay? What that means is, if we have a Young's modulus, okay, from copper to tungsten, okay, we can actually draw the graph of how basically based on the percentage or the composition of the material, how does Young's modulus change? Okay, so this upper curve represents the upper limit, and the lower curve represents the lower limit. Okay, so remember, our test data is not always perfect, and so we have a scatter of actual test samples, right? These two curves represent the upper and lower extremes of these samples. So the rule of mixture basically just says that if you're looking for the upper limit, you use this equation, which is Young's modulus is equal to the volume of the matrix material multiplied by the Young's modulus of the matrix material plus the volume of the particle material multiplied by the Young's modulus of the particle material. And if you're looking for the lower limit, you use this equation, which is 1 over Young's modulus of the composite is equal to the volume of the matrix material over the Young's modulus of the matrix material plus the volume of the particle material over the Young's modulus of the particle material. Okay. Why would you want one over the other? Well, if we want it to break, we might want to look at what that upper limit is. If we don't want it to break, maybe we'll want to look at what that lower limit is. Okay, that's kind of the idea. Because we want to be conservative when we're designing things. We don't want things to break prematurely. So we follow our test data, right? We're looking at that very extreme of the test data. We're saying we're not going to try and design below this curve. Okay, and this also has application for other properties as well. So electrical conductivity, we can replace the Young's modulus in these equations with our sigma e's. So that's a value of electrical conductivity. Then we can also, for thermal conductivity, we can replace the e's in the equations with k's. Now, we have not discussed in this course electrical conductivity and thermal conductivity in detail. These are topics that we talk about in this course when we do this in a full semester, but you will learn a lot about electrical conductivity and thermal conductivity in other courses. So for the sake of the summer course, I decided to remove these from the curriculum. But this is in typically what we cover. So, but yeah, this is a very nice, nifty equation where you just substitute whatever your material property is with basically the material property that you want, right? So we replace our Young's moduluses with thermal conductivity or electrical conductivity, or it could be some kind of optical material property or corrosion material property, etc. Okay, so now we're going to move into fiber reinforced composites. So fibers are very strong in tension. Okay, that's what's great about fibers. As you might know, you take a rope and you pull on it, it's going to resist that. But if you put that under compression, it's probably not going to do as well unless you hold it, right? Well, in matrix materials, you're actually holding the fibers on every single side. So your fibers become columns, essentially. So when you push on them, they're going to be stronger than if it was just the matrix material alone. So just because they're fibers doesn't mean they're going to be all noodly when you push on them. So these provide significant strength improvement to the composite. They're usually always made of stiffer material than the matrix, which lets you save weight usually. So for example, fiberglass, these are continuous glass filaments in a polymer matrix. So glass fibers have really great strength and stiffness, but the polymer holds the fibers in place, protects the fiber surfaces from corrosion, and transfers load to the fibers. We have different kinds. So there's whiskers. These are thin single crystals, and they have large length to diameter ratios. Okay, so they're they're short, thin little whiskers. These can be made of graphite, silicon nitride, silicon carbide. They have usually high crystal perfection, so they're usually extremely strong, and they're also the strongest known types of fibers that we can use. But they're very expensive and they're difficult to disperse because, you have a gazillion little whiskers to throw around perfectly into your matrix material, so it's going to be more difficult. We have fibers, so you have to love how we have the fiber types, and of the fiber types, fibers are a type. But these are your longer standard fibers that you would see, like these up here that we talked about before. These would be considered fibers. Okay. And so these are polycrystalline or amorphous. Okay. They're generally polymers or ceramics. And I would maybe disagree just slightly with that. I think that metal fibers are common, like the kinds of materials that I worked with. Like we would have metal fibers sometimes, but they're saying that they're generally polymers or ceramics. That's fine. Alumina, aramid, e-glass, boron, and I'm not sure what UHMWPE is. And then finally we have wires. Okay, and yeah, they're including metals in this case with steel, molybdenum, and tungsten. But your wires are usually going to be a bit thicker than your fibers will be. Fun fact about fibers: there is a really popular material. I'm not going to say the name of it because that will unfortunately add a huge amount of stigma to the conversation. But there's a certain material that's extremely controversial. That is kind of like a space age material. Like, it's a phenomenal material. Really excellent. And it was used around the 50s or 60s all the time. And what was cool about it was it was actually ceramic material, but it was extremely fibrous. And so it was extremely resistant to flame, so you could actually protect buildings from burning down. People would use them in tiles on the floor. You'd put it on the spaceship to protect it, and even in clothing, you could even put it in clothing. But usually, like, they were found all over in buildings, like office buildings and things like that. Well, the problem with this material is if you actually break into this ceramic material that I'm talking about, the fibers would actually go airborne, and you could inhale them into your lungs, and that would actually cause cancer over time. Okay, and that material was asbestos. I couldn't think of the name, so I actually had to pause and go back and look for it. But yes, asbestos, phenomenal space age material of the future. Engineers love it, but unfortunately, it does cause really bad effects in humans, and so we had to stop using it. And so you can't find asbestos used anywhere in the United States today because, well, I shouldn't say that. There's probably certain limited cases where it is still used, but very rare and very heavily controlled and regulated at this point. So that's something to keep in mind when you're working with composites. So it could have unintended consequences. All right, so we're going to talk about fiber alignment. So I talked about this a little bit before, but we can have a discontinuous. So this is a discontinuous fiber. Notice when I say discontinuous, what I mean. These fibers do not connect all the way through the material. They are chopped, but aligned. Well, they're saying they're continuous, but in my opinion, they're still pretty much discontinuous. An actual continuous fiber composite should go all the way through the material, or a great distance of the material at least. Okay. Whereas in the discontinuous sector, we can have an aligned discontinuous, okay, versus a randomized chopped configuration, okay? So notice in our longitudinal direction, how strong should this be? And it should be pretty strong, right? Because that's where our fibers are aligned to. Our fibers are the ones that are carrying most of the stress. But in the transverse direction, if we were to pull this way on it, it'll be much weaker, right? In this discontinuous and aligned system, you'll have the same idea. It's going to be stronger in this direction, but weaker left and right. But in our randomized scenario, where they're just randomly chopped and sprinkled sporadically, like I would say actually the density of them should be relatively the same throughout the material, but the orientation must be perfectly random, which means it really isn't random at all, but like many different orientations for the fibers. What this does is it actually adds strength in all directions. So now we have an isotropic material. Is that right? Well, isotropic in 2 dimensions. Let's put it that way. It's not isotropic in all 3 dimensions, but it's isotropic in 2 dimensions for a thin sheet like this. Now, in our 3D printer filament that I was talking about before, that really is randomly configured in all 3 directions. So it is isotropic for all intents and purposes. Okay. So we have fiber reinforced composites. So we have some examples of aligned and continuous fibers. So here what we can see is these are actually aligned and continuous fibers that are sticking out of a matrix material. So this is like a gamma nickel and aluminum compound mixed with an alpha phase of molybdenum. And so we can actually grow these crystals of nickel and aluminum in a single direction. And then from that growth, we can actually have alpha phase of molybdenum forming around it. Okay. So this would be a pretty advanced material. And then here's a glass with silicon carbide fibers. Okay, so here we have a ceramic matrix with silicon carbide, which is also a ceramic fibers that are inside of it, and this is formed with a glass slurry. So you actually have molten glass that you form around these fibers, and then you let it solidify. The Young's modulus of the glass is only 76 gigapascals, but the silicon carbide has a Young's modulus of 400 gigapascals. So this adding the silicon carbide actually adds to the stiffness of the material quite a bit. And you can actually see where it broke here, which is very interesting. So here we actually see an example of what's called fiber pullout, where if you actually see fibers being pulled out of the material, it actually means that it did not bond well to the surrounding matrix material. So when composites break, if you have fiber pullout, it means that your interface, which means the contact strength between the matrix material and the fiber material was not very good. And if the fiber actually perfectly breaks in a straight crack, for example, it could mean one of two things. Either your fiber material was too stiff when you put it in there, like it was made improperly, or it could just mean that everything worked perfectly, right? Okay. So here we have discontinuous fibers. So these are random in 2 dimensions, and this example is carbon matrix fiber. And so carbon is what they're calling it, but we have that's right. So it's carbon fibers, which are very stiff and very strong, in a carbon matrix, which is less stiff and less strong. And they're saying it's a polymer resin matrix, which I wouldn't. It must be some kind of polymer carbon, which I mean most are hydrocarbons, right? But there must be a really high amount of carbon in whatever repeating unit that they're using. And this polymer resin is pyrolyzed at up to 2,500 degrees Celsius. Okay, so basically this resin is set at a really high temperature because it's mostly carbon. And this is used in disc brakes, gas turbine exhaust flaps, and missile nose cones. Okay, so it's a very high temperature material because that's what you need for example, disc brakes and missile nose cones. So our carbon fibers, okay, so yes, and then also our fibers lie on a plane, okay, and then these planes are stacked one on top of the other to create the actual body of the material, okay. Other possible uses, these could be discontinuous and random 3D. So basically, these are 2D random, but they could be made in a 3D random orientation. That you can't stack that. If that's the case, you cannot stack a random 3D system. You would have to set it all at the same time, which we see in some composites, for example, like our 3D printer filament. It's set immediately once it's placed. And also, it can be discontinuous and aligned, right, which we've already discussed. There is a critical fiber length for effective stiffening and strengthening. So if we take our ultimate tensile strength and our fiber diameter and our shear strength of the fiber matrix interface, this should be less than this. This system, or this value that we get from these inputs should be less than the fiber length. Okay, so once the fiber length goes over this value, then we have reached our critical fiber length. So that's exactly how long those fibers need to be to get the most out of our system. If they're shorter than that, we're not going to get the most out of our fibers. It's like getting more bang for your buck, right? You want longer fibers in your system, or at least long enough to surpass this value. So for fiberglass, the common fiber length is a bit over 15 millimeters. For longer fibers, stress transference from the fiber is more efficient, okay? So for your short and thin fibers, and what we see here is actually these small fibers are being pulled in the matrix, and this is representing how much stress is being transferred into the fiber. And you can see here that we actually have a low fiber efficiency, meaning these straight lines, there's very few compared to the number that are distorted here. Whereas with a longer fiber, we have higher fiber efficiency, which means it's carrying more load because it's longer, okay? So compared to the distortion that's being caused by the end of the fiber, there's a lot of straight lines essentially in between, showing that the stress is being carried. So for continuous fibers, we can estimate the fiber reinforced composite modulus of elasticity. Okay. So to get that, we basically just take our Young's modulus, and again, this is exactly what we've seen before with our particles, with our particulate matter, except instead of saying EPVP, we're saying EFVF. Okay, so for Young's modulus of fiber multiplied by volume of fiber, or I'm sorry, volume fraction is what that should be. So it's just, the amount of volume of one over the other. So these actually, if you add VM and VF together, they should equal 1.0. So here are ECLs are longitudinal modulus of the composite. That's why it's ECL. And E sub m is our Young's modulus of the matrix. V sub m is the volume fraction of the matrix. Okay. Okay, and so in transverse loading, the fibers carry less of the load. And here, we would actually use what we were talking about for the lower curve. Okay, so remember we had an upper curve and a lower curve for our particles. Here, we would just use the second equation for the lower curve when we're talking about a transverse loading scenario. Why is that? Well, it's kind of like we're talking about a it's kind of like we're talking about a particle system now. If we're looking along that direction, right? If I were to draw you a line and tell you where the fibers were along that line, but those fibers are oriented transversely to the line, then they'd just be dots, right? So essentially particles. And so that's why we're using the particle equation here, or like, okay? And again, remember, I told you that this can substitute for other material properties as well. So keep that in mind. You don't have to just use Young's modulus here. Okay. So we can also estimate for discontinuous fibers. Okay. So this is valid when our fiber is less than 15 times our value, right? So these are what we consider discontinuous. Otherwise, we consider them continuous. Personally, when I think of that terminology, I think that continuous fibers should mean almost all the way through your material, because that's what I've worked with in the past. But we can talk about how, in terms of efficiency, as far as efficiency is concerned, this is where the point between continuous fibers and discontinuous fibers separate, and that is when our fiber length is less than 15 times the value that we're talking about, or the value of our material properties for the fiber. And so our elastic modulus in the fiber direction is now the same equation. Okay, it's the same equation, but now we have this efficiency factor K that we have to deal with. Okay, that efficiency factor is actually coming from the orientation of our discontinuous fibers. So if they're all aligned, K is equal to 1. Okay, we just say these are basically like our they're basically like our continuous fibers, okay? But if they are aligned perpendicular, so basically in the transverse direction to loading, then K is equal to 0, okay? Basically meaning that our fibers almost mean nothing in this case, okay? Also, if we have a randomized 2D system, two-dimensional system, we say K is equal to 3/8, okay? We call it 2D isotropy. And then if we have a random 3D system, it is K is equal to 1/5. It's actually less if it's a 3D system, okay? So you give up a little bit, right? You actually give up some things when you're talking about a randomly oriented fiber orientation. Okay, so we can estimate the strength of these composites for the discontinuous fiber system. So when our length of our fibers is greater than the critical length for these fibers, then we can say that the strength of the composite, okay, is equal to the fracture strength of the fiber multiplied by the volume fraction of that fiber multiplied by 1 minus the critical length over 2 multiplied by the actual length plus the critical stress of the matrix multiplied by 1 minus the volume fraction of the fiber, okay? And that 1 minus volume fraction of the fiber, what does that mean? It's actually the volume fraction of the matrix material. And now, alternatively, when our length is less than our critical length, then this other equation applies, where we're now using our length multiplied by the shear stress divided by d, the diameter of the fiber, multiplied by the volume fraction of the fiber, plus our stress for the matrix material, multiplied by the volume fraction of our matrix material. Okay, so here's some composite production methods that you might be interested in learning about. So one of them is called pultrusion. Okay, so this is very common when making long fiber composites, so continuous fiber composites. Continuous fibers are pulled through a resin tank. Okay, so we've got this tank right here filled with resin. It's like think about it like a bathtub. We've got our fibers that are on what's called rovings, but they're like spools. We pull all of the fibers together, and then we pull them through this resin. Okay, so basically these fibers all get coated with the resin. Then they get put through a preforming die, which forms them into a certain shape. Then they're pulled through a curing die, which actually cures the material and hardens it. And then they go through the actual pullers. Okay, what this means is if you have really large fiber rovings and you have a lot of material in your tank, you can make this entire composite material continuously. You just keep pulling. The more you pull, the more material you make. And of course, you have to have a certain amount of time it goes through the curing die, right? Let's see. Yes, and the steel die preforms them preforms them to the desired shape. This preformed stock passes through the curing die, and then it's precision machined to impart the very final shape in the curing die. So there's a little bit more shaping that's going on here, and then it's heated to initiate the curing of the resin matrix. So that's what I said basically, but I didn't add the fact that this curing die is actually also adding to the shaping of the material. Okay. We can also have a filament winding procedure. So this is also like continuous fibers, but now we're talking about winding them, okay? And this is done quite a lot actually with tubes. So if you use composite tubes, in fact, if you look quite a few lessons ago when I was talking about the composite tubes that I would work with, those were wound in the same way. Ours were, I believe, helically wounded. Okay, we didn't. I think they were helically wounded, and then they did another winding of circumferential. They didn't really do polar. So these continuous reinforcing fibers are accurately positioned in a predetermined pattern to form a hollow and usually cylindrical shape for winding. Fibers are then fed through a resin bath to impregnate and with thermosetting resin. These impregnated fibers are continuously wound, typically automatically, onto a mandrel. So this thing would be the mandrel. And then after appropriate number of layers are added, kind of like I talked about with my composite material, curing is then carried out in either an oven or at room temperature. In the case of our silicon carbide composites, they were put in something called an autoclave. An autoclave is like a super oven, okay? It's an oven that can go to really, really high temperatures. And then finally, the mandrel is removed to give the final product. So once it's cured and it's set, you just pull the mandrel out and the material will remain stiff. Okay. So you'll think about, like, if you think about, some of the stresses that we talked about before. In mechanics of solids, we talk about hoop stress and longitudinal stress quite often. And you can kind of see you would do polar winding to try and improve your longitudinal stress in this tube. And then you would do circumferential winding to improve your hoop stress. Okay, so then here are our structural composites, okay? So our laminates, these are our laminates, and it's kind of like what I described before, but these are stacked in certain orientations. So you could have a stacking sequence like 0 degrees, 90 degrees, 0 degrees, 90 degrees, and alternate that way. Or you could have 0 degrees, 1 degree, 2 degree, 3 degree, all the way up to 360 degrees. Or really 180. You could go up to 180 because you don't really need to go all the way around again. And then you could even have 0, 15, 30, 45, all the way up to 90. And so these are actually quite often used in aerospace materials. And if you ever take a graduate level composites course, which are offered in different institutions, a composites course will actually talk about how do you calculate the material properties of these kinds of laminated materials. Okay, very interesting concept. You actually have to dig really deep into your theory of elasticity to actually cover that material, and you have to do a lot of working with what's called orthotropicity. Okay, you have orthotropic material. So actually, this 0-90 degree system would be an orthotropic material, not an isotropic material, not an anisotropic material. Orthotropic. Okay, so now we have sandwich panels. And sandwich panels, you can do all sorts of stuff with these. For example, you could put a honeycomb core between two facing sheets, and this actually gives you low density with large bending stiffness, right? This honeycomb material that you put between a face sheet and an adhesive layer. Okay, so you basically just glue the honeycomb to a face sheet, basically, and that gives you a fabricated sandwich panel. And those can be very strong, right? That's considered a composite material. Okay, and then finally we have the benefits of composites, right? So if you have ceramic matrix composites, by adding fibers into them, you increase the toughness of the material. What this means is you go from an unreinforced system, okay, that's relatively stiff, but breaks quickly, to a reinforced system that now actually has higher stiffness because you've added fibers to it, but when they fail what's called gracefully, quote unquote gracefully. Okay, so now they won't just break as soon as they pass the elastic region. Now they will actually give you an ultimate tensile stress, and then following the ultimate tensile stress zone, you will have a certain amount of displacement occurring before final fracture. And then you have your particle reinforced. Okay, here your particle reinforcement actually does not help a whole lot with making the material fail more gracefully, but it does add a lot of stiffness, and it does increase your yield stress. Okay, which means right after you break, because ceramics, heavily stiff materials, they don't tend to give you an ultimate tensile stress following yield because they just break at yield, usually. So for polymer matrix composites, you get increased Young's modulus over density. So this is like a stiffness ratio. Think of it as like a stiffness to weight ratio. Some might call this rigidity, or modulus of rigidity, I think is another terminology that's used. Why would you want that? Why would you want high stiffness with low density? Okay, think about that. You want high stiffness, low density. Oh, aerospace materials, right? So for polymer matrix composites, okay, you can actually get pretty low density with really high stiffness. Okay, that's what this purple region represents. And then ceramics are more dense, metal alloys are more dense, polymers by themselves are not stiff enough. Okay, so you get good stiffness with low density in polymer matrix composites. That's your fiberglass, that's your carbon fiber. Finally, we have metal matrix composites. They give you, among other things, increased creep resistance. Okay, so if we look at our steady state creep rate on our y-axis and our just applied stress on our x-axis, typical 6061 aluminum, which by the way, 6061 aluminum is like the bread and butter aluminum. If you ever encounter aluminum in your daily life, chances are it's 6061. But if you add whiskers, it's got this curve here. But if you've got whiskers that you add to it, silicon carbide whiskers, what this actually slows down your steady state creep rate. Okay, so it means that it's more resistant to creeping. Okay, which is pretty good. So even though you're applying a higher load, it's not creeping nearly as quickly. Okay. All right.